Hey guys, sorry I'm running a little bit late. I got trapped on the toilet for a second, but we are ready to get going, so let's get going. So, pulled up two just in case. I want to talk a little bit about the homework schedule because I decided to do something slightly different than what we normally do. Because we have our first exam next Friday, it didn't seem fair or appropriate to have the homework close on Monday. So I went ahead and let the homework for this week run also to Friday of next week. That way you can work on the homework right up to the exam. And that just seemed like the fair thing to do. So homework 5, let me switch over to the .cam here. Homework 5 will be due. All right, so yeah, so homework 5 will be due next Friday instead of next Monday. Normally it would be due on the Monday after it opens. But because next week is our first test and that test takes place on Friday, it only seems fair to let you work on the homework right up to the day of the test. That is what felt appropriate. It's also a slightly longer than usual homework. It's about the same length as the homework from last week. So I just want to make sure you have sufficient time to get it done. I don't want you to feel rushed. I did get a few emails requesting specific problem types. So before I move on to talking about the product and quotient rules, which is the normal topic for today, or the planned topic for today, I wanted to go back and solve just one more of these problems where you're graphing f, and then from the graph of f, you're expected to graph the derivative. So we're going to do one of those, and then we'll move back to our differentiation rule stuff, our chapter 3 stuff. Specifically today, we're going to talk about the quotient and product rules. All right. So a quick example from section 2.8.
Professor, could you exit out of the pop-up menu for the
Sure, sorry.
.cam whenever you can? Sorry.
Here we go. Thank you. All right, so your homework from last week had a few problems like this, where you're given the function f of x, you're told to graph it, and then from that you're expected to come up with the graph of f primed, the derivative. I want to look at just one more of those. So we could have it be from the homework. I have one in mind that'll let us talk about something cool. So and then if there's anything like this from the homework that you guys specifically want to do, we can do that too. Okay, so we're going to graph the function x to the 2/3, which maybe is a function you remember from your algebra classes, maybe not. It's not a super common function to encounter in those classes. And then we're going to use the graph of f to sketch the graph of f primed. And then from there, I want to make sure that we're comfortable with the relation between the two, right? We want to make sure that we really understand how the graphs are connected, because that's going to be a big, big deal moving out of chapter 3 and into chapter 4. First, this guy, he's a power function. The power here is smaller than 1, but it is positive. So if I'm starting to try and get a graph of f of x, depending on how much you remember from your algebra classes, we can say that in quadrant 1, this graph looks something like the square root function, right? What it really is, x to the 2/3, that's the cubed root of x all squared, right? You can write it like that, or you could put the square inside. So in quadrant 1, it has a shape kind of like this. Right, kind of like the square root function. You're going to take all the outputs from the square root or the cube root function, which in quadrant 1 looks like that, and then square them. The cube root function on its own is an odd function, and it continues over here in quadrant 4 like this. But since this guy is squared, he's actually going to be up here like this. So this function is an even function. It is symmetric about the y-axis, or its graph is symmetric about the y-axis, I should say. It looks something like that. If I want to figure out what the graph of f prime looks like, well, maybe we should plot a few points. No, I don't want to clutter the graph. The shape is enough. The shape is enough. The point 1, 1 is on here if you like. And what else is nice on there? 8, 4 is on there. That would be way out here, so I'll just leave it like that. Notice that this function from -infinity to 0, everywhere on this side, is decreasing. So what can I say about f primed from -infinity to 0? If f is decreasing, then what is true of f primed? Maybe I'll start down here with some notes.
Would f prime be increasing?
Not necessarily.
Approaching 0?
Decreasing.
You might want to look back at your notes. This would be a good time to refresh the relationship between f and f primed. Negative, yeah, Diana got it in the chat there. Since f is decreasing on -infinity to 0, f primed is negative on -infinity to 0. And over here, f is increasing, which means f primed will be positive. So f prime will be positive. Right, so remember, f increasing means f primed is positive. F decreasing means f primed is negative. The derivative is the slope of the tangent line, right? So if I look at a place where the function is decreasing, like right here, and I imagine drawing in the tangent line would look something like this. In particular, it would have a negative slope, right? And the slope of the tangent line is f primed. So imagine drawing in a few tangent lines. Over here, the slope is negative, but it's not as steep as it is here. We're getting steeper and then steeper. So these slopes are the y values of f primed. So here, that slope looks to me to be like -1/2 or something. Here, maybe the slope is -1. Here, maybe the slope is -2. Which means that the y values on the graph of f primed are going to be these slopes. I'm just approximating. But let's mark this here as -1. Continue this y-axis down a little bit here. Mark that as like -2. So over here, where the slope of the tangent line is a little bit negative, the graph of f prime should be a little bit negative. Over here, where the slope of the tangent line is a little more negative, the graph of f prime should be a little more negative. Over here, where the slope of the tangent line is more negative still, the graph of f prime should be more negative still. And what you notice is that on the graph of f, as we get close to the origin here, my tangent lines are getting more and more vertical. That slope is actually vertical right here at 0. It's going straight up and down, which means f primed, remember, a vertical line doesn't have a defined slope. But these slopes are getting more and more negative. They're getting larger and larger, and they are all negative, which means that f primed is going off to -infinity there. So here's a reasonable sketch of the graph of f primed from -infinity to 0. All right, so the blue is f, and the pencil is f primed. Big fat points. The y value here is the slope there. The y value here is the slope there. The y value here is the slope there. That's the idea. Since these slopes are getting more and more negative, these y values are getting more and more negative. Does that make sense?
Yes, can you zoom in just a tiny bit?
Say that one more time.
Can you zoom in just a tiny bit, please?
Sure, yeah. Is that better?
Yeah, thank you.
All right. Let's play the same game, but over here now. If I were to sketch the tangent line right about here, that slope to me looks to be, I don't know, about 1/2, maybe 1, something like that. It's definitely a positive slope, right? We're going uphill. And it's definitely not as steep as it is like right here. And over here, it's positive, but more shallow still. So what's going on with f primed over here? Well, over here, f primed is positive, but small. Positive, but bigger. Positive and bigger still, right? This tangent line has a positive slope, and it is a bigger positive slope than this tangent line. So maybe here m tan is about 2. Maybe here m tan, the slope of the tangent line, is about 1. And maybe over here m tan is about 1/2. Again, just really, really vague approximations. So if that's 1 over there, then let me bring this up a little bit. I knew I was going to need space. I didn't know I was going to need that much space. So if that's 1, then 2 is like right here. If that's 1, then this is about 1 right here. Yeah, actually, it's going to go like that. And if that's 1, this is like 1/2 right here. So the graph of f primed on this side looks something like this. And again, as we get closer to the origin here, where the original function is getting really, really steep, right? The original function f there, remember, looks like this. So right here, at that cusp, it's called, the tangent lines get really steep, which means the y values on f prime are going to blow up to infinity. So this is a reasonable sketch of f prime based on the graph of f. Since we have better tools to examine or calculate f prime now, we can actually find it and graph it. So to follow up here, I would like to do that. First, though, questions on the graph.
So the tan of the first one in the second quadrant is the y of, bit confused there. Can you explain that one last time, please?
So the slope of the tangent line at any point along the original is the y value on f prime at that same x value. So pick
Got
a
it.
value like x equals 2. Look at the slope of the original graph at that x value. Here I said, oh, well, to me that slope looks to be about 1/2. That means that the y value on the derivative is 1/2.
1/2. Got it. Cool. Thank you.
Values on the graph of f primed are the slopes on the graph of f. That's the big idea, right? And we're used to doing that one point at a time where we calculate the derivative and use that to find the slope of the tangent line. But now I want to plot all those slopes as y values, and that gives me the graph of f primed. And that's what's going on in homework 4, right? You've got like 6 or 7 problems where you're given the graph of f and you're asked to sketch the graph of f primed. This is how you do it. You take a few points on the original function, and you estimate the slope of the tangent line there. It doesn't have to be perfect because we're really just trying to get a shape. After you have a few points where you say, oh, well, here the tangent line looks to be like -1/2, here the tangent line looks to be like slope -1, here this tangent line looks to have slope -2, then you plot at that same x value, the y value -1/2, the y value -1, the y value -2. Those points are points on the graph of f prime. Hell yes, there is. So Caleb asks, is there a way to do this with algebra? Well, yeah, mostly no. There's a way to do it with calculus. So that's where I want to follow up. But before we do that, I want to make sure we're comfy with where the sketch came from. Because this is an important skill. On its own, this is an important skill. So pick a few points, approximate the slope of the tangent line. If f is decreasing, then f primed will be negative. If f is increasing, then f primed will be positive. If f is getting steeper and steeper, then f prime will be getting larger and larger in size. So as we come in towards the origin here on f, he's getting steeper and steeper, which means f primed is getting larger and larger. I use this particular function because the point at the origin there is very, very pointy. It's called a cusp. It's pointier than the absolute value function, right? The absolute value function has like these 2 lines that meet at 90 degrees. These guys are both coming in and becoming vertical. It's like a needle. It would poke you if it sat on your skin. That's called a cusp. And a cusp on the graph of f, something that's shaped like this, real pointy. That's a terrible sketch. a cusp, something like this, on the graph of f, where the tangent lines get vertical, that's called a cusp. Okay, there are a few questions in chat that I want to address, and then we'll talk to Angelica for a second, and then I'll show you the actual for sure graph of f primed. So let me see, what was the question in chat? Where did the y values on f primed come from again? So the y values on f primed are the slopes of the tangent lines on f. So if I want to know where did this y value on the graph of f primed come from, I come up here to the graph of f at that same x value and ask, what's the slope of the tangent line there? At this x value right here, the slope of the tangent line on f appears to be about -1/2. That means that the y value on f primed there is -1/2. All right, Angelica, you had a question, yeah?
Yes, thanks. So does the cusp and the vertical asymptote correlate, or is there none and it crosses the y-axis?
No, that's you nailed it. The cusp on f gives the vertical asymptote on f primed. That is exactly the connection I was hoping you guys to make. Yeah, because the slopes of the tangent lines here get vertical, and a vertical line has infinite slope, right? You're used to saying a vertical line has undefined slope, but if you think about it carefully, a vertical line is the same thing as a line with infinite slope. These slopes are getting steeper and steeper. They're getting larger and larger. And in the limit, as you approach x equals 0 here, the slopes are getting vertical. And in this class, the easiest way to interpret that is by saying the slopes are infinite. And that is the vertical asymptote you see here for f primed, right? F primed kind of looks like this hyperbola with this vertical asymptote at x equals 0. That's coming from the cusp. So that's a beautiful observation. Thank you, Angelica. Other questions about how we're getting the graph of f prime, the pencil graph? Okay, it's important that you remember these two comments. F decreasing means f primed is negative, f increasing means f primed is positive, and the converse is true. If f primed is negative, that means f is decreasing. If f primed is positive, that means f is increasing. Now, if I wanted to be a little bit more quantitative, rather than just guessing these slopes, I can calculate f primed. F of x is x to the 2/3. So we're going to answer the question, is there a way to do this like with algebra? Is there a way to do this for sure? Since f of x is x to the 2/3, by the power rule, f primed of x has to be 2/3, we bring the power down, times x to the 2/3 minus 1, right? We bring the power down and then subtract 1 from the power. That's 2/3 times x to the, if I take 1 away from 2/3, I get -1/3. In other words, f primed is the function 2/3 times the cube root of x. This little 3 here is hard to see. 2/3 times the cube root of x. So I'm going to flip over to Desmos now and graph both of those. So here's the graph y equals x to the 2/3. It's got that pointy cusp, and it kind of looks like a square root sort of thing over here. And here's the green graph, looking like that hyperbola, looking like our pencil graph. You see it? Red is f, green is f primed. And the connection there is that the slope here is the y value here. And as you come in towards the origin, these slopes are blowing up to infinity, which means that the green graph, f primed, is going to have a vertical asymptote there. Okay. So I wanted to walk through one more of these because I know a lot of people are still working on homework 4. I hope that this helps a little bit. If you're having trouble with any of those questions, please come to the office hour or send me an email with a picture of your work or something so we can discuss them. But I really want you guys to grasp this all the way. There's one other thing we need to do before we can start talking about the product and quotient rules, and that's to address how we find derivatives of exponential functions, which are super duper important in calculus, especially Calc 1. So it's the last topic from section 3.1. And if there aren't any other questions on this example, I'm going to move to that now. So are there any other questions on this example? Okay. This is the continuation of section 3.1. Last time we learned the power rule. Today we're going to talk a little bit about derivatives of exponential functions. You may remember in your pre-calculus class or even college algebra, we talk about how exponential functions describe systems where what happens next depends on the state of the current system. Like if you have a population that's breeding and growing, like a population of cells on a petri dish, the number of cells that will be there tomorrow depends directly upon the number of cells that are going to be there today, right? Because each cell will divide, creating 2 new cells. And however often that happens, the number of cells on the plate will double. It turns out that this says a lot about the rate of change for an exponential function, namely that the rate of change is always proportional to the original function. Specifically here, I want to talk about the derivative of e to the x. So the number e can be defined as the limit lim h to 0 e to the h minus 1 over h equals 1. So e is the unique number, I should say maybe defined by the limit. E is the unique number that makes this true. Remember, e is about, I know you've all encountered this before, It's an irrational number, about 2.7. This is called Euler's number. Or the natural base. You can say that E is defined by this relationship. It's the only number you could put here, so that if you raise that number to the h, subtract 1, divide by h, and then send h to 0, that limit comes out to 1. This is actually how your textbook defines the number E. It's a little bit frustrating to me because I know you guys have seen other definitions of E in your algebra classes, but I'm not sure you remember them. We will talk about how those relationships interact in Calc 2. But for us, this is what we're going to take to be the definition of the number E. It's the same number that you played with in your other algebra classes when you talked about exponential functions. And this limit is very useful in calculating the derivative of e to the x. So before we leave section 3.1, I need to show you how to differentiate the function e to the x. And if you've taken any of those previous classes with me, you already know what's coming. Let's go ahead and just do it though. This would be the limit as h goes to 0, f of a plus h minus f of a all over h, which is the limit as h goes to 0 of, well, what is f of a plus h? If I come back here and I plug in a plus h for x, I get e raised to the a plus h. And then what is f of a? Well, that's e to the a. And all of this is being divided by h. Now I'm going to do some algebra. This is the limit as h goes to 0. Of course, I can't just plug in 0 for h, right? Because there's an h downstairs. So I have to do something. This e to the a plus h, I can write that as e to the a times e to the h, right? If you multiply like bases, you add the powers. So e to the a times e to the h, that's the same as e to the a plus h. And then I still have this minus e to the a, and it's all still being divided by h. And now I've got this shared factor of e to the a upstairs, which can come out. So that's the limit as h goes to 0 of e to the a times e to the h minus 1 all over h. And now this e to the a, he doesn't have any h's in him. For the purposes of this limit, this term is constant. So he can come out in front of the limit. And I get e to the a times lim h to 0, e to the h minus 1 all over h. But what is this limit?
-1?
Oh, well, compared to the very top line here.
Oh.
Yeah, e can be defined as the number such that this limit is 1. This limit is the same as this limit in the definition of e. So by the definition of the number e, this limit is 1. Which means f primed of a is just e to the a times 1. which is e to the a. In other words, the derivative of e to the x is e to the x. All right, if f primed of a is e to the a, then f primed of x is e to the x. E to the x is the unique function, which is its own derivative. That's the big deal. That's why everybody cares so much about this function. If you use any other number here besides e, it wouldn't work out quite like this because this limit would not come out to 1. Another way to say that, in Leibniz notation, we'd say that d dx of e to the x is e to the x. So e to the x is the fixed point of the differential operator d dx. It's the unique function that when you differentiate it, you get him back. In other words, the y values on the function e to the x are the same as the slopes on the function e to the x. Which is pretty cool stuff. This is not a trivial thing. This is the only function whose rate of change is the same as his output. Let's come back to Desmos for a minute. If I ask, what is the slope of the tangent line right here? According to what we've just found, that should be the same as the y value on the graph right there. So the slope is 1, which means the tangent line would be this guy. Be the unique line going through that point with slope 1. What if I wanted to find the tangent line over here at x equals 1? Can I get it? Let's see. That should be y equals e times x, because that's the slope there. And then I just have to make it move through the appropriate points. That would be y minus e equals e times x minus 1. And that's at this point 1 comma e right here. Okay. So if I look here at this point of tangency, I get this line, and what I'm paying attention to right now is the slope. The slope is the same as the y value. Just like here, the slope is the same as the y value. So the big deal here is that you remember this, right? Remember, the derivative of e to the x is e to the x. And with that, we're done with section 3.1. I'd like to do maybe one more quick example where we calculate a derivative using the power rule and this new rule together. All right, so let's see if we can find d dx of 1 plus 2x cubed minus 3 square root x plus 2 e to the x. Remember how we do this? I can take, since these are all split up by addition and subtraction, I can take the derivatives of each piece on their own. This is the same as d dx of 1 plus d dx of 2x cubed minus d dx of 3 square root x plus d dx of 2e to the x. So that was the last theorem that we discussed at the end of class on Monday, that you can take derivatives of sums and differences one piece at a time. In other words, the d dx operator kind of distributes over addition and subtraction. d dx of 1, what is the derivative of the constant function 1? Feel free to look back at your notes from the end of class on Monday. It was the very last thing we said.
Zero?
Yeah, the derivative of a constant function is 0. Now for this piece, the 2 can pop out. Constant multiples come out past the derivative operator. That was also a part of that last theorem, the linearity theorem. So I'll pop out that 2, I'll pop out this 3. And while I pop this 3 out, I'm going to rewrite the square root of x as x to the 1/2 power. And then I'll pop this 2 out. So that first piece differentiates to 0 because it's a constant function. The rest of the pieces I can rewrite as either power functions or basic exponential functions. So what do we get? This 0 goes away, so I'll have 2 times, what is d dx of x cubed?
6x squared.
Very good, yeah. By the power rule, this is 3x squared. And then I'll have minus 3 times, what's the derivative of x to the 1/2?
Square root of x.
I'd say 1/2 x. Well, 1/2 minus 1. So what would that be? Negative 1/2.
So the power comes down, and then I'll have x raised to the 1/2 minus 1, right? So it's the power rule. Just like here, the power came down, and then we took away 1 from the power. So 3 times x to the 3 minus 1 is 2. Here, let's just write it like this for now, and then we'll clean it up later. Yeah, it's going to be negative 1/2. And then here I'll have 2 times, what's the derivative of e to the x?
E to the x.
E to the x, yeah, that's the piece we just sorted out. Okay. And then maybe the last thing to do here would be to clean this up. So this is 6x squared minus 3/2 times x to the 1/2 minus 1, which is x to the negative 1/2, plus 2e to the x. Okay. So any questions on any one of these steps?
Why is d dx times 1 0?
Let's take a look. So that's a theorem that we stated but didn't prove. So let me remind you, the theorem from the end of class last time said that d dx of f of x plus or minus g of x is the same as d dx of f of x plus or minus d dx of g of x is the same as the derivative of f plus or minus the derivative of g. We had this. We had d dx of a constant times f of x is the same as the constant times d dx of f of x, which is that constant times f prime, so constants pop out. And then the last thing was that d dx of a constant all on its own is 0. The proof of 3 is pretty straightforward. If f of x equals c is a constant, then f primed of a is the limit as h goes to 0, f of a plus h minus f of a all over h. But if f of x is a constant, then f of a plus h is just c. So this is the limit as h goes to 0 of, this would be c, this would also be c, and it's all over h. So this is the limit as h goes to 0 of 0 over h, which is the limit as h goes to 0. Forget about the limit for a second. Oh shit, here, sorry. So we're going to prove 3. If f of x equals c is a constant function, then f primed of a is, this is the limit that always defines f primed of a. But since f of x is the constant function c, f of a plus h is c, and f of a is c. So this numerator in this difference quotient here is always 0. So that's the limit as h goes to 0 of 0. This function here is equal to 0 no matter what value you plug in for h. And the limit as h goes to 0 of 0 is 0. So this is the direct proof, but there's another way to interpret this. What do the graphs of constant functions look like? Like the function f of x equals 2 or f of x equals -5. What do those look
A
like?
line.
What kind of line? You're right.
Vertical line.
A horizontal.
Horizontal line, sorry.
And horizontal lines have slope 0, right? They have a
Yeah.
constant slope. The slope is 0. The derivative gives you the slope of the tangent line, right? So if you're looking at a horizontal line, then the tangent line, no matter where you look, always has slope 0. So the derivative of a constant function is always 0 because its rate of change is always 0. It's never changing at all.
Cool.
And this is a big deal. There's a few problems in your homework that are designed to sniff this out. They're designed to be a little bit tricky. So this is a good thing to remember. The derivative of any constant function, always 0. If you look along the graph of any constant function, the tangent line is always horizontal. Does that make sense? Is that a satisfying response?
Yeah, I'm following now.
Any other thoughts on these or questions? So another way to say this is that the differential operator ddx is a linear operator. And if you do go on to study things like linear algebra or higher mathematics, the study of linear operators is a big deal, especially if you're into like quantum physics. Quantum physics all about linear operators. The differential operator is kind of your prototype linear operator. Okay. Any other questions that relate at all to this example? How we found any of those derivatives, or how we knew to break it up, or why anything worked the way it did? Here, I'll move this so if we're still looking at the theorem, we can see both. Okay then. So then I'd like to begin 3.2. That is the end of 3.1. Let me make sure I'm not missing anything. I don't think I am. We will talk about derivatives of other exponential functions, like 2 to the x and 5 to the x, but not until we have the chain rule, I believe. We need a trick for those. Do they do this? I don't think so. There is a way to force it, but do it through natural exponential function. Yeah, no, this is good. All right. So product and quotient rules, section 3.2. So we know that the differential operator ddx splits up over addition and subtraction really nicely. It can like be distributed. But what about over multiplication? What if I wanted to differentiate something like x squared times e to the x? It turns out that you cannot just differentiate each on their own and then multiply the results. That does not work. So what is not true this is not equal to ddx of x squared times ddx of e to the x, unfortunately. If that worked, that would be nice and everything would be easy. But also, if that worked, then calculus wouldn't be what it is. It would be boring. It turns out we need a little bit more care to do something like that. Now, your textbook does offer something of a proof, but it's messy, and I don't really want to scare you. Where can I get a nice argument here? Let me just show you the result. I think you will interpret this better if I just show you the result. So what is true is the following. called the product rule. And it says if you want to differentiate a product, the nicest way to write this is in the prime notation. So here's how I'll write this. d dx of f of x times g of x, that is the derivative of the product f times g. I'm going to write that using the prime notation as f times g all primed. Remember, there's like 3 or 4 different notations for the derivative. The prime notation is the nice notation for a lot of things. So these two just say the same thing, right? The prime is the same as saying d dx. The way this turns out, you differentiate the first guy and leave the second guy alone. And then to that, you add what you get by leaving the first guy alone and multiplying by the derivative of the second guy. There are picture proofs of this that are okay, but I've never really seen a proof that gave me a lot of intuition. I'm not aware of a nice proof. I'm not aware of a proof that is at our level worth spending class time on. It is important that you remember that you cannot just differentiate each of them on their own and multiply. This is 100% necessary. I can try to find you something that looks like a decent picture proof. I know like 2 or 3 proofs, but none of them are nice in the sense that they give you some sort of intuition. Yeah, so here's what we have, right? F times g prime is f prime times g plus f times g prime. There's a standard picture that goes with this, but it's not here. Now, you see all this is, it's always just this mess of symbol juggling. It's not fun. The closest thing to a nice proof, yeah, looks about like this. So you've got here your 2 functions, they're calling them v and u. And if you want to know how much does this rectangle change as u and v both change a little bit, you have to keep track of how the one affects the other. That's this little green, how the other affects the one. But it's, again, it's not super intuitive. This one appears to be a little bit prettier. Yeah, so u times v is this rectangle. And we want to know if I nudge the input for each of them a little bit, how does the overall thing change? Well, you get a little nudge from v here. You get a little nudge from u here. And so the overall change to the rectangle, you pass from this to this whole thing. I don't expect anybody to find this really satisfying at this point. Unfortunately, the proofs of the product rule, the best one I could give you at this point would be the textbook proof, where we look at the difference quotient. And then that is just a whole bunch of symbol juggling. It's not a very pleasant thing. So maybe what I'll do is I'll post a video to Canvas where I go through the proof of this theorem. It would be the standard proof, the same proof that's in the textbook, and it's just a bunch of symbol juggling with the difference quotient. I would like for us to get practice with it. This is a skill building class. We need to get good at doing things, not so much at stressing about why the theorems are true. But the truth is, the reason why the theorems are true is super important. Unfortunately, this particular theorem, there just isn't a nice proof of. It's a little bit hard to understand. So look in the modules under Canvas a little bit later today. I should have that up by around 3 p.m. For now, let's see how we use it. So at the start, we asked, how could I differentiate x squared times e to the x? if I call this piece F, and I call this piece G, then I see that x squared times e to the x, all primed, should be f prime times g. That's x squared primed times e to the x, plus f times g primed. So that's plus x squared times the derivative of e to the x. So you differentiate the one, leave the other alone, and then add, leave the one alone, differentiate the other. F prime times g plus f times g primed. The derivative of x squared is 2 times x to the 2 minus 1 is 1. So I get 2x times e to the x. And then here I have my plus x squared times the derivative of e to the x is just e to the x. So this is how we use the product rule. If I wanted to do something like find out where this thing has horizontal tangent lines, I could then work with this derivative. I could factor e to the x out. And I get that. I could factor an x out. And I get that. So just for fun, let's take a look at the graph of this thing. I don't know what the graph of x squared times e to the x looks like, but let's play with it. Here it is. That's the graph of x squared times e to the x. And let's also look at the derivative, which is e to the x times x plus 2. So the blue is the derivative of the red. Maybe I'll put the blue in this dotted format or this dashed format. So you see where the red is increasing, the blue is positive. And then right here at -2, the red goes from being increasing to decreasing, and the blue goes from being positive to negative. If we keep going along the graph of the red function, right here at 0, he goes from being decreasing to increasing, and the blue goes from being negative to positive. So everywhere the red is increasing, the blue is positive. Everywhere the red is decreasing, the blue is negative. The x-intercepts for the blue graph are places where the red graph has turning points. That's a big deal. Places where the red graph changes from increasing to decreasing are places where the blue graph changes from being positive to negative. Changing from positive to negative means x-intercept. So x-intercepts for the derivative are turning points for the original. And this is a nice function to illustrate that. I could have found those turning points by setting this derivative equal to 0. If I set this equal to 0, e to the x is never 0. But this factor is 0 when x is equal to 0. This factor is 0 when x is equal to -2. So the blue is 0 when x is 0 and when x is -2. And those are the turning points for the red function. That's one of the main applications of the derivative, is finding turning points, finding minima and maxima. But for now, we're just practicing the product rule. Any questions on this calculation? Okay. Your homework has lots of things for you to practice on. I want to introduce one more concept before I hit you with the quotient rule. Or maybe I'll hit you with the quotient rule and then we'll introduce that concept. Let's do the quotient rule first. No, we'll go ahead and talk about higher derivatives first. So the topic of higher derivatives is a little bit awkward to choose where to introduce it. We could have introduced it right away at the start, but it's nice to have some skills first. So now that we have some skills, I will show you this thing. We can differentiate more than once. So you give me a function, say find the derivative. Okay, well that derivative is itself another function. So I could find its derivative. And I just want to show you the notation for that before we move too far. So if you apply the operator ddx to the original function f of x, you get out the derivative, which we call f primed of x. If you apply the differential operator to f primed of x, you get out its derivative, which we call f prime prime of x, or f double prime of x. If you apply the differential operator to f prime prime, f double prime, you get f triple prime of x. And the nicest place to talk about these is in the setting of physics. Your original function may describe the position of an object moving along a straight line. Say something just thrown up or down. Then the derivative of that is the velocity. How is your position changing over time? That's your speed, right? Your velocity. How far did you go divided by how long did it take you? And in the infinitesimal limit, we call that the instantaneous rate of change, which is your speed or your velocity. What if I ask, how is your velocity changing over time? Has anybody ever thought about this? Suppose you're driving in your car and you want to speed up. That means you want to increase your velocity. What do?
You accelerate?
Accelerate.
You accelerate. That's exactly the word I'm looking for. So in physics, if your position is s of t, then the derivative d dt of your position, s of t, or s primed of t, is called your velocity. And we write s primed of t equals v of t, v for velocity. The second derivative of position, s prime prime of t, which would be d dt of v of t, or v primed of t, is how your velocity is changing. And like we just said, if you want to increase your velocity, we call that acceleration. So this is called acceleration. And we write for S double primed, which is the same as V primed. We call that A of t. So this is the most intuitive way to think about the first two derivatives. If your original function is your position, then the derivative, the first derivative, is your velocity, how your position is changing. The second derivative, S double primed, is how your velocity is changing, or V primed. We call that your acceleration. So how's your position changing? That's your velocity. How's your velocity changing? That's your acceleration. There is actually a name for the next step, S triple primed. It's called jerk. And then some very silly people at MIT came up with snap, crackle, and pop for the fourth, fifth, and sixth derivatives, respectively. But it's these first two that you need to know well. So these three functions, S, V, and A. These are position, velocity, and acceleration. V of t is S primed. A of t is V primed, which is the same as S prime prime, the second derivative. And thinking about speeds, like traveling in your car, this is the easiest way to gain an intuition for what the derivative really is. So there's one or two problems in that homework 4 that have you tackle things like this. And I just wanted to introduce the notation and talk a little bit about higher derivatives before we get too far into chapter 3. It's worth noting that both velocity and acceleration can be negative. If your velocity is negative, that means you're going backwards. If your acceleration is negative, what would that say about your velocity? Remember, acceleration is the derivative of velocity. So if your acceleration is negative, that means V primed is negative. What does that tell you about V?
V is also negative.
I'm sorry, I heard two things there at once. It's not true that V would be negative, but it is true that V would be decreasing, right? If your derivative is negative, then you are decreasing. So if your acceleration is negative, then your velocity is decreasing. In other words, when you hit your brakes on the car, you're slowing down. That means your velocity is decreasing. That means you're experiencing negative acceleration. You hear people talk about this when they talk about the experience on a roller coaster, the experience that fighter pilots go through in their jets, positive acceleration and negative acceleration. In your car, positive acceleration glues you to your chair. If you've ever been in a fast car, when you hit the gas, you get thrown back into your chair. Negative acceleration is when you hit your brakes and you're pushed forwards. So if your velocity is increasing, then your acceleration is positive, because acceleration is the derivative of velocity. And if your velocity is decreasing, that means your acceleration is negative. What would it mean if your velocity was equal, let's say this. What would it mean if your acceleration is equal to 0?
You aren't moving.
So that's if your velocity is equal to 0, right? If your velocity is equal to 0, you're not moving at all. But what if
You're moving at a constant speed?
Constant speed, right? So if your acceleration is 0, that means your velocity isn't changing at all. What does it mean for your velocity to not be changing? It means you're moving at the same speed. You're not speeding up or speeding down. So there is at least one problem in homework 4, I think maybe just the one, and one problem in homework 5 that asks about the relationships between S, A, and V. And I really encourage you to think hard about those as you get to them. I'm making notes here just to post some things to the modules to let you have a little bit more fun and get a little more comfy with these. All right, so this is the notation for higher derivatives. If you take a derivative of a derivative, we call that the second derivative, or f double prime. If you take a derivative of a second derivative, you get the third derivative, or f triple prime. You can, of course, keep going. If you want to differentiate the third derivative, eventually your hands get tired of writing the prime, right? You kind of run out of space up here and it starts to look silly. So for here and on, we use this notation. So this would be the same as f with 4 primes, but that kind of looks silly, doesn't it? So instead of writing the 4 primes there, we put a little parentheses and a 4. And for all higher derivatives, we write this. You won't encounter these a lot in this class. We'll talk about the first and the second derivative, but we won't talk much about the third, fourth, or any higher derivatives. For example, the fifth or sixth derivative would be f6 of x. I have one problem in your homework that has you dealing with a high derivative, so you need to be aware of this notation. And then in Calc 2, when you talk about Taylor series, you'll use that notation quite a lot. So let's wrap up. I'm going to just show you the quotient rule, so those of you who are ahead in the homework can get started on that. And then next time we'll do some examples with the quotient rule, and we'll also look at the derivatives of some trig functions. So I should say this is a theorem, the quotient rule. If I want to differentiate a ratio, like f of x over g of x, just like the product rule doesn't let you differentiate each piece on their own, in a ratio, you cannot just differentiate each piece on its own either. We can, however, get the quotient rule from the product rule, but that would require the chain rule. So a direct proof of this is going to have to wait. I will just give you the result. And then on Friday, we will start with some examples of this. The derivative, d dx of a quotient, a fraction, where the top and bottom are both non-constant functions, which we could also just write as f over g all primed, is g of x times f primed of x minus f of x times g primed of x all over g of x squared. It's a little bit complicated. The way people remember this, there is a mnemonic. If we call the bottom function here low and the top function here high, then the quotient rule says that the derivative of that quotient is low d high, so the bottom times the derivative of the top, minus high d low, the top times the derivative of the bottom, all over low low, the bottom squared. So low d high minus high d low over low low. For some reason that sticks. So if I wanted to differentiate something like x squared over e to the x, I would need to use this. Unfortunately, this is where we run out of time for today, so we're going to have to wait on for examples for tomorrow. And then once we have the chain rule, I'll be able to prove this for you from the product rule. I have notes here to post a nice proof of the product rule, or at least the nicest proof I can find of the product rule for you to Canvas. And also some videos discussing the physics and the relationship between position, acceleration, and velocity. So look back at our Canvas modules page sometime after 3 p.m. today, and I'll have that stuff up there. And
Will you be holding office hours today?
say that one more time.
Sorry, will you be holding office hours today?
Yeah, I have my normal office hour from 1 to 2. So I have one other class to teach right after this one. And then I'll have office hours from 1 to 2. And then that is when I'll start assembling that material for you guys on Canvas. So that should be up by 3.
Thank you.
Of course. Any other questions before we head out for the day, guys? Any sections of the notes you would like me to throw back up so you can copy them, or anything that we missed?
Actually, yes. It was the beginning of 3.2, the product and quotient rule, right around there.
No? This guy?
Which page? Yeah, thank you.
Of course. Let me know when you need me to move it up or anything.
Have a great day.
Sir,
Thank
when
you.
are you gonna release the guide study?
The study guide I will send out on Friday. So after our next class, I will send out the study.
Okay, thank you.
Of course. Anything else, gang?
When you get a chance, would you show me higher derivatives, that page? There's a last part on the bottom that I wasn't able to write fast enough.
Sure.
Thank you.
Yeah, of course.
And then just the bottom of the one you were just on for the beginning.
Ready?
Thank you.
So how about this? I think she wanted the bottom of that page, you want the bottom of this page. So let's try like that. Is that working?
Just be
Yeah.
Yeah. Thank you. And then whenever she's done, can you just give me the whole page so I can double check it? Sorry, I'm exhausted today.
No, that's
Thank you.
fine.
I'm done. Thank you.
Okay, so back to this page.
Yeah, just make sure I didn't stuff it up.
Sure. No, you're good.
Thanks. Okay, perfect. Thank you so much.
All set? Alrighty then, I am going to go ahead and end the meeting here for today. I'll see you guys either in office hours at 1 or on Friday. I hope you have a lovely afternoon. Remember, keep working on that homework. The study guide for exam 1 is going to come out Friday, so you want to have as much of the homework done as possible. That is it. See you later, guys.